Okay, hello everyone. My name is Narendra Hermawan, and today I'm going to explain about signal propagation and path loss models. What actually is propagation? Propagation is how the signal propagates from transmitter to the receiver. There is propagation characteristic. The path loss is the path loss represent the blue line. The path loss itself is the fall off relative to the distance, and there is shadowing, which represent the red line. Shadowing is random fluctuations due to obstruction, and the last one is multipath, which is flat and frequency selective fading caused by multipath. So as you can see here from this figure, the Tx is Pt and the Tr is Pr. The strength of the signal is what it identifies it. It is constant for transmitter power, but not for the receive power. The receiving side receives a better signal when it is stable. As we can see from the figure, the right figure, the y-axis depends on the receive power because transmit power is constant, as I mentioned earlier, and the x-axis depends on the distance between the transmitter and the receiver. As the distance increases, the receive power drops exponentially. This is indicated by the blue line. From there, the red block represents an object that creates a non-line of sight scene. The graph shows the intensity of the receive power change as shown by the red line. When there are multiple refraction due to buildings, wall, and other things, changes in the receive power will produce a certain ripple effect. The scenes of this colored line are also represented by blue path loss, red shading, and green multipath fading. In telecommunication, predictable signals are the key to how much power the receiver has to compensate. And this is the path loss modeling. So there is Maxwell equation, phase space, and two path models, ray tracing models, single slope path models, exponent models, and measurement based and standards model are among the answers presented. The Maxwell equation looks at the interaction of the electric and magnetic fields, which are combined to form electromagnetic transmission. It is, however, extremely difficult and ineffective. As a result, simpler techniques such as free space and two-path models must be utilized. And this is the free space loss model. So this is the free space model. Free space model is typically used for an unobstructed loss signal path. So this is the equation for the receive signal is as we can see here from this slide, and the equation for receive power. So the power falls off of proportional to the ratio of wavelength over distance speed. The inverse frequency dependence is due to the effective aperture of the receiver. The power falls off proportional to the next antenna gain, and this model is not accurate for general environments. And the next one is two-path model. So, yeah, the ray tracing approximation represent the wavefront as simple particles, and the simple model only determine reflections, and the scattering and diffraction can also be included. And into path model, there is one lost path, one reflected path. There is one lost path and one reflected path, and at small distances, power falls off proportionally to the free space loss on both paths. And from this slide, we can see the equation for the receive power. Yeah, as we can see. So the above the E, the power falls off proportionally to the D powered by 4, and it is independent of signal wavelength. And this model is not generally accurate for cities or indoors. And the next is general ray tracing. So in general ray tracing, it incorporates all signal components, including reflection, scattering, and diffraction. The reflected ray have power fall off proportional to d square by free space path model. Scatter and reflected ray have more power fall off that depends on exact distance of scattering or refractive object from transmitter and the receiver. If objects are more than a few wavelengths from the receiver, typically neglect scattering and refraction, and most computer package for channel simulation in indoor or outdoor environments use general ray tracing for path loss, and this model requires detailed site information to work effectively. The next one is simplified path loss model. The simplified path loss model is the simplification version of the path loss model. It is used when path loss is dominated by reflection from objects gamma, and it is the most important parameter for the path loss exponent, and it is determined empirically. Gamma range from 2 to 8, and the R, or the receiver location, and the D represent the reference point to the receiver location, and the PR is power received, and the PT is power transmitted. And the last one is the empirical model. So there is few problem with all this method, and this method generally used to solve a certain condition for a certain location or other thing. So the first one is the simple analytical path loss model. It is used for irregular terrain like cities, and doesn't lend itself to a simple, yeah. And the second one is the empirical path loss model based on extensive measurement. And the next one is local mean attenuation. So it is an empirical measurement of local received power. The next one is Okumura model. It is used for empirical model that place in irregular terrain. The next one is Hatta model. It is analytical approximation to Okumura model. And the next one is cos231 extension to Hatta model. So basically it extends Hatta model to 2 GHz and to lower mobile antenna height. Widely this model is widely used in 2G simulation. The last one is visualized linear models. It captures multiple slopes associated with path loss. Okay, that's it for my presentation. Thank you.